Hello everyone. Uh, so this is day 2 of binary exploitation, and this is part of the InCTF training series. So without much waiting, we'll just start off with the contents. What are we going to do today? So we'll go through the quick recap of what we did in day 1, which is just yesterday, and we'll be solving two challenges today. One is red to win, but with arguments, and then another is red to shell code. If you didn't already watch the previous stream's content, which is Red to Win, Rohit really explained it really well in the day 1 session of binary exploitation. So today, what will we cover? We will cover calling conventions because I feel like we didn't cover it that extensively in the previous session. Cool. So this is binary exploitation, right? So why not let's just create a sample program which includes the library. I'm pretty sure you know what a library is from the previous session. And in the main function, we can see number is 1337. And then it is calling printf with hello chat and the number. So if you compile this program with GCC and then you run it, it should technically say hello chat 1337. What basically is calling convention? As the name suggests, we will just see what happens during a specific call, or in this specific case, call of printf at PLT. So I have made the sample program. Let's go into the calling convention directory. Yeah, so I have made this sample program, right, which you just saw right now. We'll just compile it. In order to compile, you just give GCC with the source and tag O for saying the final output name of the binary. Let's run the binary, and it says hello chat 1337. Okay, let's boot this up in GDB. And let's just start with the main program. So this is the main program. And you can see the entire disassembly here of the main function, which you just saw here. So in order to go to the next instruction, you just click NI, which just stands for next instruction. Okay, now in the disassembly, we have reached the call function, which is a call to the printf, and which you should already know it's part of the library. The calling convention basically says that when you're calling a function, the first argument will be in RDI, and the second argument will be in RSI, and the third argument will be in RDX. So printf has two arguments as you saw here, which is hello chat %d and number. And string can't directly be stored in RDI, right? That's why you have a pointer pointing to the string saying hello chat %d. And in RSI, you have OX539. Okay, but here it was 1337, right? Basically, this 1337 is OX539. It's just the base conversion. So that is that. And as Rohit explained yesterday, what happens during a call? When you SI or step into it, the next instruction after the call will be pushed onto the stack, right? So the next instruction here was 175, and that was pushed onto the stack. So that once printf gets over, you can come back to the main function and continue your execution. So that is basically calling convention. In order to simply put calling convention, you just have to know the arguments to a function. Essentially, when you call printf of argument 1 and argument 2, what happens is RDI takes your first argument, RSI takes your second argument, and RDX takes your third argument. Now, if anyone's watching the stream right now, what if there is more than 3 arguments? You can, of course, Google and just say what you want in the chat. Okay, I think you guys have enough knowledge to maybe solve a red to win. but with a twist. And the twist is there are arguments, because you learned about arguments now. Let's exit GDB. Let's go to red to win with arguments, and let us see this file. I'll open it in code for better view. Okay, so we have the C file and the binary file given. Let's understand what happens in the C file. Again, we have included the library, and this is just a comment saying how our source file is being compiled. Then, of course, we see our good old win function. But it's not just a win function that calls execv. It has win function and some kind of a check that says your arg1 has to be this and your argument 2 has to be this. Okay, we'll come back to that. And then you have your main function, which has a buffer of OX60 and some puts and a printf. That is basically doing %p of buffer. We'll see what that is later. And then it has a gets. If you would have already attended the session yesterday, you should have known what gets is. Gets, it basically reads a line from std into the buffer until there's a terminating new line or an end of file, right? Now, where is the problem there? Our buffer is just OX60, but the amount of input that a buffer can take through gets is not defined, and it's arbitrary. So you can take how much ever you want, and there you have an overflow. Basically, this is an overflow. So let's just compile this program with the comment I gave here, and I'll explain you what this does. Simply put, you want to change this, right? Red to win with arguments. Let's call it red to win with arguments. And you are basically making the stack executable. The stack is where your static variables are stored, right, during function calls, and where your function frames are stored. And then you have NoPy, which I would like you guys to Google and find out what it is. And then you have fno stack protector, which will remove the canary. Okay, right when you compile this, you already see a warning message saying gets is really dangerous, and it's a function that you should never use. But yeah, me being a really bad developer, I've created this code with gets. So let's exploit it. So you can skip most of the part here. Okay, fine. You can skip most of the part here. You can use any normal font tools methods that Rohit told yesterday. So we just try triggering the gets now. SL is basically send line, and you are connecting to the program called red to win with argument, and then you are sending a lot of A's just to see what happens. So let's run this program. Exploit, and in order to trigger GDB debugging, we just give the GDB option. Now there is no libc, so cool. So what happened here is we triggered the return. So if I'll take a quick session on what exactly happened here. So you have the stack here, right? And when you call a function from main, let's say this is main's stack frame, right? When you call another function, say A, what happens is you store the return address here, right? And then you store whatever variables you need for the function A. And now you see where the bug is, right? If in function A, if you're allowed to use gets, you can overwrite all of this, including the return address. So when you're exiting out of A, what happens is you don't go back to main, but instead you go back to something else that you defined, or basically what you overwrote here. That is the gist of it. And pretty sure you would have covered it yesterday. But that out of the way, I guess we'll move further. We know the buffer is OX16. And then you have the RPP. What is P64? It's nothing but packing your data that you give to the function to convert it to Little Indian. As you know, everything in the stack is Little Indian. So when you write some data, it gets stored like this, right? You can think of it like that. So we pack the data there. And then finally we give the win function's address. Now, how do we get the win function's address? Let's go to GDB, info func. Info func will give you all the functions that are there. And there, we got the win function's address. Let's copy that and just paste it here. Okay, let's see what happens. And before that, I actually want to set a breakpoint. In order to see the main function's disassembly, you just type this as main. And I want to stop right here and make you guys understand what exactly happens. Okay, so this does a breakpoint right at the return in the main function. So let's quit GDB, run our exploit with GDB. Okay, it stopped right at the return, and let's see what happened. Tell or telescope just prints out a lot of stuff from the address that you give. So I just want to inspect what happens before ROX50. And you see all of our A's are there, right? This is all of the A's that we wrote. This is the RPP that should have been there. And then we overwrote it with our win function. So for context, we are right now at the return address going to jump to win function. So let's just go there, step into, or you can just type next instruction and keep going until we see something. Okay, so there's a compare instruction that checks if it is not equal to, it will just leave. Okay, so we'll see what happens then. It is comparing our RDI and RSI, which is basically the 32 version is EDI and ESI. So 4 bytes of our memory is put somewhere, and then it's getting checked with some value. And you might be familiar with that because we just saw it here. Our argument, which is RDI or EDI in this case, should be equal to OX deadbeef, and ESI should be equal to cafe babe. So okay, now we can trigger the win function, but how are we going to set the values to RDI and RSI with the corresponding values of deadbeef and cafe babe? That's what we are going to look at right now through the concept of what is a rob gadget. So what is your motive here? In simple terms, your motive is you have control of the return address, right? From this, what you have to do is make RDI equal to OX deadbeef. And what do you do after that? After this, you make RSI equal to OX cafe babe, right? And then what do you do? And then you call win function. It's as simple as that. You have to do return address first, set RDI to OHZBeef, set your RSA to cafe web, and finally call the win function, so that all of these checks will be satisfied, and you can call execv of winsh, which would land you a shell. So let's see how we do that through the help of ROP. And if you would have been listening carefully, we have been chaining a lot of stuff, right? And how are we chaining all of this? Is through return addresses. So what happens is you do some work like pop RDI, which basically pops what is on top of the stack, and then you return. And this return address again takes what is on top of the stack and jumps there. And hence the name came ROP, return oriented programming. So yeah, that's basically it. So what you have to do is you do some work and you use the return address to do the next work, and then keep going until you reach the win function. Now, how do I find these ROP gadgets? It might be your next question. So we have a tool for that called ROP gadget, which you can simply install by searching for ROP gadget, install, and yeah, from this GitHub page, you can simply install ROP gadget. And this tool basically runs through your entire program and prints out all the possible gadgets that your binary has. Okay, so now these are all the gadgets that your binary has. And what are gadgets? These single instruction that do specific work is called a gadget. So for example, call RAX in this case is a gadget. Add ESP8 and return is also one gadget. Likewise, all of these are gadgets. Now, what is the specific gadget that we were looking for? We were looking for pop RDA, right? To win with R. Okay, so we'll just use ROP gadget with the binary option and then call it on red to gadget. Okay, so like I already told you, we need to set RDI, right? And the easiest way to set RDI is just pop RDI. So let's search for pop RDI here. Pop RDI. Oh, how nice. We already have a gadget here for pop RDI. So what we can do is, let's store this here. Pop RDI is at the address of this. What else do we need? We need to set RSA, right? So let's see if we have RSA. Okay, pop RSA, but we have another pop along with it and then a return. So we'll just store this as pop RSI and reg. Cool. Now let's try calling pop RDI. Again, you have to pack it to little endian and pop RDI. And this time we'll give some value and let's see what actually happens. Okay. Let's give 8 A's and see what happens. Again, let's run this with GDB. We'll see. My bad. Okay, so a really important lesson here. Now, there is obviously a binary, right? It says it's an ELF, but I don't seem to able to run it. But it definitely is an executable, but it says it's not executable. And the reason is simple. It's just this is a file that is an executable, but it's not given the permission of execute. So what you do is just chmod to give it permission, and then you run the binary, and it works. So let's run the exploit with the GDB, and let's see. This is the name. Okay. So we came to the return address, and like our exploit should be doing is calling the pop RDI gadget that we just found out, right? So we'll jump to the pop RDI, and pop RDI, what it basically does is it will take this value and put into RDI, and then it will return to whatever is the next instruction. Let's see that in action. Pop RDI just got executed, and you can see RDI is OX 41414141, which is basically A's, and then you return. But we didn't really give anything after those A's, right? And hence there is nothing here, and we would just seg fault, or we would go to some memory that literally doesn't exist. So we know what we are doing. So we will chain this return to go to the next gadget, which is return oriented programming. Pop RSI P64. We wanted to give RSI as this value, right? And RDI as this value. So let's just copy and let's just put it there. This is Cafe Babe, and this is supposed to be OX dead beef. OX dead beef. Okay. Now let's run this. We can see that pop RDI works, and then my bad, I continued instead of next instruction. So okay, so we have the pop RDI, which will put OX dead beef, and then it has returned. It will return to pop RSI. We'll see that. Pop RDI takes the topmost value, which is dead beef, and then return takes this value, which would jump to pop RSI, and pop RSI would take the topmost value of Cafe Babe. And pop R15 is just popping the topmost value onto R15, which we really don't care. So we can put any value that we want. And then after that, it returns again. Now you see where we are going, right? We use the final return to jump to the win function. We can just give any value like junk, and we can jump back to the win function. And we don't know the win function, right? Let us find out the value of win function. Win function is here. Okay, now let's run our final exploit that we created with GDB. it does return pop RDI, pop RSI, pop R15, and R15 becomes junk. And then we return to win function. Let's see if the compare works right now. It does a compare and it doesn't jump to the not equal to condition. And it says you're awesome. And you are. So we reach the exec VA, which says bin sh of 0 and 0. And there we get a shell. So if this binary was posted somewhere in the server, you would have easily gotten a shell and you would have earned the title of a hacker. Who am I? I am Torpran. So that is it with the first challenge, and all you had to know was just how the arguments work and your knowledge from a red to win session from yesterday. And what is a ROP gadget? It might be a little confusing, but if you start doing more challenges, I don't think it'll be that hard for you guys because you're all smart. Now let's look at shell coding, because you know what the next challenge is, red to shell code. So in shell coding, we are doing a lot of concepts like syscall, setting registers, and somehow reach the shell code, right? Too many things going on. But in simple terms, whatever you saw there, like in this case, the red to win with argument, these are assembly instructions. From your C code, it gets converted to the assembly instructions, and these get executed, right? Now what we are going to do is we will have the control over what we are going to execute in this challenge. And because we passed on the flag of no executing, when we were compiling, we put the compilation flag as exec stack, which means if you are running this, when you do check sec, which is basically checking the security of the program or the mitigations, it says that it has a stack that is executable. And if you do VM map or the virtual memory mapping, which basically is like all the storage that you use when you are running the program, and the program in itself gets stored here, that is the red to win gets stored here, and your libraries that Rohit told yesterday also get stored here. And we see the stack. It has the permissions as R, W, X, and P, where P just stands for permissions and RWX stands for read, write, and execute. Now you see where the problem is. If we have some malicious code in stack, we can just execute it if we have control flow over there. So you would ask, why would you need that? Because we already have a win function. Now, if I do this, that is remove your win function and compile it once again in another directory, just to maintain the challenges, I'll copy this here, red to win with arguments. So we are going to name this red to shellcode .c. We can close this because we have successfully completed red to win with arguments. Let's open this, and like I told you guys, I have removed your win function. There is no more winning for you guys. So how are you going to get shell on this program? That's exactly what we are going to be doing now through these. Let's do a quick recall. In yesterday's session, you guys took what is a syscall, right? In a really vague idea, syscall is just where you want to execute something really important, and it just switches the control from a low privileged guy to a high privileged guy, more like from the user to the kernel. And you also need to somehow reach that shell code, right? And that is why this is called return to shell code. and not return to win. So yeah, and you have already learned about setting the registers with the help of your pop, and we'll see how to do with the help of assembly or shell coding. Now let's go ahead and compile this. Red to shell code. And it again says gets, because of course now you would have been really familiar with this warning, and if you see a gets, you can hack it. Let's run the code, and this time it's saying, for now I'm gonna tell you a secret, and it shows some really weird number. Let's just boot this up in GDB and run it. Okay, so I'm gonna tell you a secret, right? Let's just see what this number is. I want to do X info on it because I feel like that is an address, and X info just gives me all the details of what it is. So it is basically a stack address, and you know what? Stack is executable in this program. Okay, so that is fine. Let's connect the dots here. You know the challenge is ret to shell code, right? You already know how to return to some arbitrary function like win, right? But in this challenge, you don't have win function, but you still have the promising idea of returning to somewhere, right? And as the name suggests, you just return to the shell code. As easy as that. But where is our shell code is the next question you will be asking. And as simple as it can get, you just write it. You write your own shell code and jump back to that. So let's see how we do this. Let's run the program and give a lot of A's. And we have to set some breakpoints somewhere. Let's set a breakpoint at the return, and let's run with a lot of A's. It didn't really crash because maybe we have to give a lot more A's than we expected. Okay, now it crashed. Now you have to observe something. You know that you have to return to your shell code, and the shell code will probably will be located in the stack. So let's see what is in the stack. How convenient. It is our input that is stored in the stack. Now let's just switch the way in which we are seeing the stack. You see stack in a way that you store something, right? Now you have to be in an angle where you think the stack is a place where your shell code will be executing. So we can do something like x/20i and do this, which means it will be expecting as instructions at the did it go just now? Okay, so we had small network issue because I'm in my college right now. Okay, so yeah, we'll continue again. We left off where we were giving our input, right? Which is basically a lot of A's, 4 A's and 4 B's. And let's just see corresponding to the address that this binary is showing you. Let's do telescope on that. Okay, how convenient. So what actually is happening here is it's just red to shell code. Let me erase all of that. Okay, so you are running a program, right? And this program is giving you a stack address. right? And in this stack address is where your input is stored. Remember how I told you you can return to anywhere like a win? This is your opportunity to actually grab that win. You can just return to your input, and which can be considered as the shellcode. So let's just start right now. Clear. Okay. So I'm loading the program of red to shellcode, and all of this is not required again. Okay. Let's just receive until where we get the I'm gonna tell you a secret so that we can grab this function and store it in our program. So let's grab all of this. I want to receive until that, and then I want to receive the line because this entire thing ends with a new line, and I just want to store this address. And I want to strip it because the new line will also be received in receive line. Let me pass this to the int function. And what base is this? This definitely doesn't seem like an integer. So this is of base 16, and that is our stack leak, right? Cool. We have our stack leak. Let's just print it out for our own sanity. I'm going to print the stack leak as hex. And there we go. It prints it out as hex. So we successfully got our shellcode's address, right? Now all we have to do is write our shellcode. And for this, I'll give you a small hint by saying you can refer to Chromium docs, or more like Chromium syscall table, to get all of the numbers, right, for the syscalls. I'll go over quickly what a syscall is in simple terms. You have the syscall, right? It's basically a call where you, as the user, can't do it, and you're telling the kernel to do it with specific numbers. Like, for example, if you give 0 as your RAX to read, to syscall, it does a read function or a read syscall. When you give RAX as 1 and you call syscall, it assumes that you're trying to do write. And you see where this is going, right? Likewise, each syscall has got its own number, like 0 to a lot, because life is really complicated, right? Yep. So we just want to have our execv shellcode, right? Which is right here. So let's grab up some information and just put it there. Let me just put it here, somewhere here. Yeah. So points to note. We have our execv as our target. Execv is the syscall that you want to execute. And in order for that, you need OX3B. And where do you need OX3B? In RAX. So RAX register has to be OX3B. What else? And your file pointer, that is, you need RDI such that you need it to point it to bin sh, not just bin sh, /bin /sh with a null character. And you can currently ignore this and just make it 0. So if these three conditions are met, your exec will run perfectly, right? So let's start creating the shell code. We need our shell code, which will be assembly. Okay, so ASM basically converts your shell code that you write into bytes. And this is a part of Pon tools. So first things first, we need RAX to be OX3B, right? So let's just put that. Move RAX OX3B. Now I'll give you like 3 to 4 seconds to guess what you would do for RDI and RSI. Yeah, I feel like you guys are stuck, so I'll just explain. Yeah, you can't directly store binsh string as it is into RDI, right? You need a pointer that points to the string that has to be in RDI. And only then the computer knows or the CPU knows that you want to execute the program called binsh. So we'll just leave that for now and we'll try to put RSI as 0. Move RSI 0 and then syscall. Okay, now we'll come to the RDI equal to binsh part. We have to store this string somewhere, and we know that our input goes directly into the stack, right? It directly goes into the stack. So why not just put your binsh string also in the stack and dereference it from there? Why not put it in the stack is what I'm saying. So in order for that, we just make bin sh string. I'm creating a label for that saying /bin /sh. Let's see how this goes. Before setting up RDI, we'll just see where the binsh string is. Okay. There's a small problem. We didn't send anything. So what we have to do is we send something, which is basically our shell code. Okay, now that we send our shell code, we'll see what happens. Okay, we'll set a breakpoint here. My bad. Apologies. We'll set a breakpoint right here, which is basically the return address. Because that is the point where your control flow changes. You change from main directly to your shell code. Okay. Now let's just go back and see. Where your shell code is. Let's do it right after gets, before the leave. Okay. So what we can see here is we can see our binsh string is there, and we have to inspect this or whatever was given to gets as instructions, right? Let's just what happened. Okay, let's just put a breakpoint right at gets and see where our input is getting stored. I keep going back to nano because that's my go-to editor, kind of. Fine. We know this is the place where our shellcode is going to be, which is, yeah, when you cross verify, that is the case. So let's just input the thing, and then now let's look at it. Okay, it's a lot of random bytes along with the string binsh. And like I told you guys, let's inspect the memory as instructions and not as storage. Basically this address. Okay, so what you can see is it is doing move RAX to OX3B, move RSI to 0, syscall, and bad. Bad is basically not an instruction, but I think on the GDB couldn't identify what it is because it's a string binsh. So now we have the shellcode, right? We have the shellcode, partial shellcode, because we didn't put the RDI yet, and we can control the return. Now we just have to basically do one step, finish our shellcode, and merge this return back to our shellcode. It's as easy as that. So and one instruction that would allow you to basically put the string into RDI. It's just the RDI, load effective address, RDA to P plus binsh. Let's see if this works. Okay, so the compiler is smart, and moreover that the parser for font tools is really smart. When you put binsh, it automatically redirected, I mean not redirected, but changed binsh to the relative address here. So RIP is just the next instruction plus the binsh offset from where it is currently there, which is basically this. So when you do RIP plus 2, it comes to here, and when you do x/s on that, you see bin/sh. How cool is that? So our shell coding problem is over. We just did RDI, RSA, and RAX as that should be working, and we'll just try to get control of the return address now. How do we do that? We don't know the size of the shell code, right? So let's just print the size of the shell code by saying length of the shell code. For now, let's comment out sending it, and let's just run this and see. Okay, so it says 31. So 31 bytes of shellcode is being written, right? What we can do is we can write the 31 bytes of shellcode, and we can send a lot of padding is to OX60 is basically the buffer size, and you add RBP to it, and you subtract 31. Okay, now let me do a quick drawing so you guys understand. You had your stack, right? What has happened is you have your shellcode here, which does move RAX OX3B, move RDI pointer to something, and so on. And what we do is we keep writing a lot of A's until we fill all of the buffer, and then finally hit the return address of the main function, right? So when you overflow all of this and then override this with something, you just need to get the win function, or you need to get shell. How do you do that? You override this so that you jump back to here. Does that make sense? Because this essentially is our shell code that we have created, right? So all we have to do is just fill this buffer and change the return address back to the shell code. Let's just do that. Plus P64 of the stackly. Now let's try running the exploit. Huh. The error says you can't concatenate the string to bytes. Basically, the shell code which has been produced by ASM are in the form of bytes, and even P64 is in the form of bytes. So, sadly, Python 2 to Python 3 conversion has caused this. So, you just convert the normal string into byte string. So, yeah, let's run it. And right now we are in the gets. Let's just do next instruction and see what is the what are the current state of our shell code. So the current state of our shell code is you move RAX as OX3B, move RSI as 0, and then you move RDI as the address. And then finally you call syscall. And then you have a lot of push A's, and then if you keep going, finally you have this, which should have been our return address. Let's keep going. Finally, when we came to our return address, it is showing a stack address. It kind of looks vague, but you know that is our shell code. It is executing RAX, RSI, and RDI. So right now we are at execv, and how does the compiler know it's execv? It is because of RAX, which is set to OX3B, and right now in the syscall state, you do next instruction, and you get a shell. Let's get the shell. Oh, am I? Sure, friends. So that is all for red to shell code, and I hope you guys understood the concept of how a syscall works and what a syscall number is and what are the register that you are setting during a syscall, and somehow how are you reaching to the shell code, which is red to shell code, right? So yeah, I'm too late for this slide already because we have already completed red to shell code. If you guys have any doubt, feel free to put it in the chat. So yeah, that's about it for this stream. And I guess this would be the last stream for this entire series, and hope you guys had a really fun time watching as much as we loved making it. Cool. Okay, bye bye.